let's look at the third searching and sorting problem from CSES. This one's called Ferris wheel. So there are n children to go to the Ferris wheel, and we want to assign them to gondolas. Each gondola can have 1 or 2 children, and the total weight cannot, there's some total weight limit. So given the weight of the child, we need to figure out the minimum of gondolas we need. So each child has a weight, and then we have the weight limit of the gondola, and we'll promise that no child weighs more than the weight limit of a gondola. So it's always possible, right? We could just assign every child to one gondola, but maybe we can do better. So how do we actually do this? So consider the lightest child. He has to go in some gondola, and we might as well try and put someone in with him. And we might as well try and put the heaviest possible kid that we can in with him, right? Because I don't know. Once you put one child in a gondola, right? The heavier the children are, the more problems they're going to be. And so if we have this free space, we should put the heaviest child that we can fit in it. And by the way, if we have the lightest child and there are some children who can't fit in with him, they're not going to fit in with anyone else either. So because he's already the lightest child, so they might as well just get their own gondola. So we can do this by sorting the list of weights and going through from the top, from the bottom, and keeping track also sort of from the top. And so as we go through each child on the bottom, starting from the top, try and assign the heaviest child that we can in with him. And eventually those two will meet, and then we're done. So let's do that. We're going to have a vector, we're going to have algorithm for sorting. We want stood. X, and we want the weights of the children. And this will keep track of the sort of heavy children, and we'll go to the light children. So, the 2 children we're looking at are too heavy. Go down the heavy child and put him in his own gondola. And then we can put the 2 children that we're considering in their own gondolas. And we're done. So actually, no. So we need to stop early, right? We need to stop once these sort of hit each other. So we must, if the sort of light child that we're looking at is the same as the heaviest child left, then that doesn't really make sense. The heavy child is, not the same as the light child, right? That's what this means. This condition is fine. And I guess we can say that getting the termination here is a little bit tricky, isn't it? So if we happen to skip past, right, so EI is the first child that we haven't assigned on the sort of heavy end. So if I is bigger than that, then that means that we've assigned everyone. I think that's fine. I'll have to see. I'm not 100% 100% sure that that termination condition is right. Okay, it's right in this case. Let's submit it and see. I think it is right. Let's see. Cool. So that looks okay. So let me see if I can justify the logic here. Okay, so this means that the child that we're considering is heavier than. Right, so we have EI is coming down from the top, I is going up from the bottom. This means that they've like crossed, and actually we've already put child I in a gondola as a heavy child, right? Because EI is less than it, and so we put everyone in gondolas and we're done. Otherwise, even if they match, or if they match, then this will get triggered right away, right? So we'll skip this whole loop, and then we'll just put the last child in the gondola by itself. And if they don't match, then we do actually have two children that we should try and consider putting in gondolas. And if they're too heavy, then we assign the heavy child to its own gondola. Yeah, so that's the idea. So that's the problem.